two cosmic titans just crashed into each other with such violence that they literally bent the fabric of reality itself. And what scientists discovered from this cataclysmic event has completely vindicated two of history's most brilliant minds, while opening up questions that might shake the very foundations of modern physics. Imagine this: somewhere in the vast darkness of space, approximately 1 billion light-years from Earth, two unimaginably massive black holes, each weighing roughly 30 to 35 times more than our entire sun, were locked in a deadly spiral dance. For millions of years, they circled each other in an almost perfectly circular orbit, gradually drawing closer as they lost energy. Then, in a moment that lasted mere fractions of a second, they collided with such tremendous force that the impact sent shockwaves rippling through the very structure of space and time. This isn't science fiction. This actually happened, and we detected it. The cosmic collision, scientifically designated as GW250114, was first spotted in January by an extraordinary scientific instrument called LIGO, the Laser Interferometer Gravitational Wave Observatory. Think of LIGO as humanity's most sensitive hearing aid for the universe, except instead of sound waves, it listens for gravitational waves, those mysterious ripples in spacetime that Albert Einstein predicted way back in 1915 as part of his groundbreaking theory of general relativity. But here's where it gets fascinating. Einstein himself thought these waves would be so incredibly faint that human technology would never be capable of detecting them. He was almost right. The changes in distance that LIGO measures are so minuscule, they're about 1,000 times smaller than the radius of an atomic nucleus. To put that in perspective, imagine trying to measure a change in the distance from Earth to the nearest star that's smaller than the width of a human hair. That's the level of precision we're talking about. LIGO operates through a network of facilities, two primary detectors in Louisiana and Washington, plus smaller sister instruments called Virgo in Italy and Kagra in Japan. This global scientific collaboration involves roughly 1,600 researchers working together to catch these cosmic whispers. Since LIGO first detected gravitational waves in September 2015, an achievement that earned 3 scientists a Nobel Prize, the instrument has observed over 300 black hole mergers. But GW25014 stands out as something special. Maximiliano Isi, an assistant professor of astronomy at Columbia University, who led the recent study on this detection, explains what makes this particular collision so remarkable. The black holes were orbiting around each other in almost a perfect circle, and when they finally merged, they created a single black hole about 63 times the mass of the Sun, spinning at an incredible 100 revolutions per second. What makes this observation truly groundbreaking isn't just the detection itself, it's the unprecedented clarity with which scientists could study it. Thanks to significant upgrades to LIGO's lasers and mirrors over the past decade, this new observation was more than 3 times more precise than that first historic detection from 2015. This enhanced precision allowed researchers to confirm 2 major predictions that had been waiting decades for experimental verification. The first prediction traces back to 1963, when New Zealand mathematician Roy Kerr built upon Einstein's work to propose something that sounds almost too simple to be true, despite being among the most mysterious and complex objects in the universe. Black holes should be completely describable using just 2 numbers, their mass and how fast they're spinning. That's it. Everything else about a black hole's behavior and characteristics should flow from these 2 basic measurements. Yes, black holes are very mysterious and have important implications for the evolution of the universe, Izzy notes. But mathematically, we think they should be fully described by just 2 numbers. Everything there is to know about them should come from how big the black hole is and how fast it's rotating. To test this seemingly impossible simplicity, scientists took advantage of a phenomenon that occurs after black holes collide. The newly formed black hole rings, like a bell that's been struck with a hammer. Just as the pitch and duration of a bell's sound tells you about the bell's material and structure, this gravitational ringing carries information about the black hole's properties and the space surrounding it. For the first time, GW250114 provided clear detection of two distinct components of this ringing, what scientists call a fundamental mode and an overtone. Think of it like hearing both the main note and a higher harmonic when a musical instrument is played. This dual detection allowed researchers to verify that the final black hole was indeed consistent with Kerr's decades-old prediction. We identified two components of this ringing, and that allowed us to test that this black hole really is consistent with being described by just two numbers, mass and rotation, EC explains. And this is fundamental to our understanding of how space and time works, that these black holes should be featureless in some way. It's the first time we are able to see this so compellingly. But here's where it gets controversial. If black holes really are this simple, what does that say about our understanding of the universe's most extreme environments? Some physicists argue that this simplicity might be deceiving, that we're missing crucial information that gets lost when matter falls into a black hole, potentially violating fundamental principles of quantum mechanics. The second major confirmation came from testing a prediction made by the legendary Stephen Hawking in 1971. Hawking proposed what's known as the area theorem, a deceptively simple rule stating that when black holes merge, the surface area of the resulting black hole must be equal to or greater than the combined surface areas of the original black holes. In other words, a black hole's surface area can never decrease. It can only grow or stay the same. It's a profound but very simple theorem that says the total surface area of a black hole can never decrease. It can only get bigger or stay the same, Issy explains. While previous LIGO observations had provided tentative support for Hawking's theorem, the exceptional clarity of the GW25014 signal gave researchers unprecedented confidence in their measurements. They could clearly identify the early portions of the gravitational wave signal when the black holes were still separate, calculate their individual areas, then measure the area of the final merged black hole and confirm that Hawking was absolutely right. Kip Thorne, one of the Nobel Prize recipients for LIGO's development, revealed that Hawking had called him immediately after the 2015 gravitational wave detection to ask whether LIGO would be able to test his theorem. If Hawking were alive, he would have reveled in seeing the area of the merged black holes increase, Thorne said, referring to the brilliant physicist who passed away in 2018. And this is the part most people miss. Confirming Hawking's area theorem isn't just an academic exercise. It could have profound implications for one of physics' most sought-after goals, unifying Einstein's general relativity, which describes gravity and large-scale structures, with quantum mechanics, which governs the subatomic world. These two foundational theories of modern physics are currently incompatible, and understanding how they work together in extreme environments like black holes could unlock entirely new physics. Emmanuel Berti, a professor at Johns Hopkins University who wasn't involved in the study, describes the LIGO detectors as hearing aids that have been continuously improved over the past decade. We can now test fundamental principles of gravity that we could not test 10 years ago, he notes. The level of detail captured in GW25114's ringing means scientists can say with confidence that the final object behaves exactly as Einstein's general relativity predicts, which Berti calls terribly exciting. Lior Barak, a professor of mathematical physics at the University of Southampton, emphasizes just how significant this particular detection is among the more than 300 black hole merger events LIGO has recorded. He calls GW250114 particularly spectacular and notes that scientists successfully extracted two pure tones from the remnant black hole, including for the first time a clear extraction of the first overtone, a fainter harmonious sound of the ringing hole. Macarena Lagos, an assistant professor at the Universidad Andrés Bello in Chile, agrees that this represents a major milestone in gravitational wave astronomy. She points out that while current tests of gravity still have significant uncertainties, this work establishes the foundation for even more precise future detections expected in the coming years. But here's what's truly mind-bending. we're essentially watching the universe's most violent events unfold in real time. Events so energetic, they literally shake the fabric of reality itself. Before LIGO began operating, scientists weren't even certain that black holes could merge in this way. Now, we're not just detecting these collisions, we're using them as cosmic laboratories to test the fundamental laws of physics. This raises some fascinating questions that might make you uncomfortable. If we can now observe the universe's most extreme phenomena with such precision, what other assumptions about reality might we need to reconsider? Are we truly understanding what black holes are, or are we just measuring shadows of something far stranger? And if space and time can be warped and twisted by these cosmic collisions, what does that really mean for our everyday understanding of reality? As LIGO continues to improve and future gravitational wave detectors come online, we're entering an era where we can test physics in ways that were pure fantasy just decades ago. The detection of GW250114 proves that some of our most brilliant theoretical insights were correct. But it also opens up entirely new questions about the nature of the universe itself. What do you think? Does confirming these decades-old predictions make you more confident in our understanding of the cosmos? Or does it raise more unsettling questions about what else we might be missing? Are we finally beginning to truly understand the universe's deepest secrets? Or are we just scratching the surface of something far more mysterious than we ever imagined?